This video tutorial will cover our next two topics in the states of matter unit, phase diagrams and allotropes. Be sure before you start that you have all notes handouts. First topic is going to be phase diagrams. On your lecture outline, you have an x-axis for temperature and a y-axis for pressure, and you should take a minute to draw in the rest of the phase diagram. As you do so, be sure to include the three main states of matter, solid, liquid, and gas, and make sure you also clearly label the other points of interest, the triple point and critical point. So at this point, pause the video and make sure you have drawn the phase diagram. All right, hopefully everybody's had a chance to do that. Now, if you look at what a phase diagram is showing you and the information that you can obtain from it, it gives us a nice summary of which state of matter a substance would exist in at any combination of pressure and temperature. And so, for example, if you were at an area where the pressure was very high, it would probably be likely that the particles would be packed close together and forced close together, and it may be a solid. However, if you were moved to the right and cross this line, meaning the temperature was increasing, it would be possible to melt that substance and change it from a solid to a liquid. Now, two other notable points to be aware of. Triple point. You see the word triple, and obviously that implies three. The triple point is right here where the solid, liquid, and gas portions all meet, and the triple point is the point at which all three states of matter coexist. Now, that is a very unique and rare point if you really think about it. There have been plenty of situations where you have encountered two states of matter at the same time. So let's say you have a glass of ice water. Well, you've got solid and liquid in equilibrium, we could say, at the same time. Or if you were boiling a pot of water to make macaroni and cheese, you've got liquid water and also steam. But obviously there's no ice present in that water when it's boiling. So a triple point is a unique set of conditions, and we will have the unique opportunity when we work with our dry ice in a few days here to actually observe the triple point of carbon dioxide, where we'll actually liquefy it, it'll start to boil, and there will still be some solid present. So it's pretty awesome to be able to observe that. The critical point over here on the graph or phase diagram is the point at which one cannot distinguish between a liquid and a gas. And the reason we would say you can't really tell the difference, if you look at where that is on the graph, we are located in an area up here that is really high in temperature. We're on far to the right, so you would think, well, that would mean the substance would be likely to be a gas because it's got a lot of energy. However, since we're near the top of the graph, we're also at a very high pressure. And so that would force those particles to be very close together, which would be kind of make it more like a liquid. And so really up in that range beyond this critical point, you can't really clearly distinguish between the two and can't really classify it as either a liquid or a gas. In fact, the term they use for liquids in that range, and I would label that maybe on your graph, is supercritical fluid. And that's what we would have kind of anywhere in this range beyond the critical point. Now, one other important feature of this graph that you should be aware of is the solid-liquid line, which I will highlight right here. At all points along that solid-liquid line, you have solid and liquid in equilibrium, meaning you have both of them at the same time. Now, that point, the line is important for a reason it'll tell you a very specific piece of information about that substance. So if that solid-liquid line has a positive slope, and if you look at this line in this example, it goes up towards the right, so yes, it does have a positive slope. If it has a positive slope, we would say that the solid state will be more dense than the liquid state. And that's how it is for most substances. However, there is a very notable exception. Water, if you look at the solid-liquid line, actually has a negative slope. And that's important to us because we know ice, solid water, is actually less dense than water. It actually floats on the top of water. All other substances that would have a positive slope for this solid-liquid line, it would be the opposite. If we were to place, for example, a solid piece of iron in a molten lava sample of liquid iron, then the solid iron would actually sink. And we know for water that is not the case. Now it is helpful to understand these a little bit if you look at some actual phase diagrams and not just a generic one like the one on this page. And so you should take a look. You have a cutout that has these two images, the phase diagram for water and the phase diagram for carbon dioxide. And what I would like you to do is to pause the video and talk to your neighbors, talk to your people around you, and see if you can come up with a couple observations, maybe some things that surprise you, or some things that are kind of weird to you, or maybe different from between these two substances. So compare, contrast, things that kind of strike you as weird or unusual. So take a couple minutes to talk with your neighbors, and then you may start the video again. All right, so hopefully you've had a chance to compare the two and have some good conversations. Some notable things that I notice when I look at these phase diagrams. I'm going to start with the phase diagram for water, the one on the left. If you do look at the general shape, we do see that this solid liquid line indeed has this negative slope, which tells us that for water, that the solid will be less dense than the liquid. It will float. It is not that way for carbon dioxide. It has a positive slope, so solid CO2 will sink in liquid CO2. One other thing I notice about the water portion of, about the water phase diagram, is that there's a very large range over which water is a liquid, which for us as human beings is great because we do need water. We rely on it every day to stay alive. And so there's a lot of different pressures and temperatures over which we can obtain liquid water. If you look at carbon dioxide, on the other hand, we would see that it's not typically a liquid. Instead, it is typically in a lot of temperatures and pressures. It is in the gas phase. And for us, that's how we experience carbon dioxide. Now, the other thing I want you to notice is the temperatures and pressures where the triple points exist. And so if you start with water, the triple point is right here, and the temperature is just above freezing on the Celsius scale. Freezing would be 0 Celsius. So it's just above freezing, but the pressure is extremely low. Now, if you haven't taken a science class where you've talked about pressures, atmospheres is a common pressure unit that we use in science, and in the room today, and on most days, the pressure is typically around 1 atmosphere. So we would never ever experience a day in here where the pressure would drop to only 0.0060 atmospheres. That we wouldn't be able to survive in such an atmosphere. So, or in such a setting with that kind of atmospheres of pressure. Now, carbon dioxide, on the other hand, if you look at where its triple point pressure is, it's way up here at approximately 5 atmospheres. And so for us, if we're down at around 1, it doesn't really matter any temperature range. As long as the pressure is only around 1 atmosphere, the only 2 states of matter that we will experience carbon dioxide as would be solid, and then most of the times gas. And that's why when we have solid carbon dioxide, which we will play with in a few days here, we call it dry ice. It never actually melts. If you look at this triple point phase diagram, the lowest pressure that liquid carbon dioxide can exist at is 5 atmospheres, and that's over 5 times what the normal pressure is in this room. So we do have a device where we will pulverize some solid carbon dioxide and put it in this compartment, this device that we have, this contraption that we have, and we will allow it to sublime, turn right from solid to gas. And as it does that, since it's sealed, the pressure is going to start to build. And it will actually build high enough that we will reach 5 atmospheres in that piece of equipment. And we will actually be able to liquefy dry ice, which as in normal settings, we can never really observe that. So that is kind of a unique opportunity for us to be able to do that. So that is a thing to look forward to as well. So those are phase diagrams. We're going to talk a little bit about types of solids and then finish up with allotropes. So we're going to start with crystalline solids. And when you see the term crystalline, you probably recognize the word crystal is a part of that. And a crystalline solid is a solid material whose atoms are arranged in a highly ordered structure. And some really good examples of crystalline solids would be things like table salt and sugar. And if you think about sand or sugar or salt, if you've ever looked at them under a magnifying glass, you know that they do exist as little crystals. They are definitely not a powdered substance. Now, salt is an interesting one. This is kind of a picture of some coarse table salt. And if you've ever looked at it under magnification at all, you'll notice that it really is very cubic in nature. It just looks like these perfect little cubes. And you can kind of see that if you look at them in the palm of your hand, but certainly much more with a magnifying glass or a microscope. And the reason why they do look like little cubes is because at the very small level, at the level of the atom, they are made of positively charged sodium atoms, which we call cations, and negatively charged chloride ions, which we call anions. And if you look at how they are arranged, they are definitely put together in this perfect, no, I can't draw it this perfect, but this perfect little cube. And so as you look at it under a microscope, it is going to look cubic in nature because at the very smallest level, that's the way it's arranged. So crystalline solids are highly ordered. They're very predictable. If I gave you more of these Cl's and Na's, you'd be able to predict how they would be arranged. It's just like stacking up a set of building blocks. But not all solids are like that. Amorphous solids are quite the opposite. Amorphous solids lack any internal structure. There's really no rhyme or reason to how they're put together. There's, I guess, more gaps between the spaces. They're not highly ordered. They're just kind of put together in any random fashion. And some examples of materials that are considered amorphous would be glass, rubber, and plastic. And one of the unique properties of glass that I like to talk about is in the case of really old glass. Glass, I know we refer to it as a solid. You can pick up a drinking glass, you can pick up a pane of glass, a mirror, but a glass is really considered in some ways a supercooled liquid. And if you think about a liquid in comparison to a solid, in a liquid the particles are still moving and sliding past each other. Now in a glass, most people say, hey, that's a solid, you can pick it up, it retains its shape and volume. However, if you look at a really old piece of glass, now this is an image looking through a window at Fort Snelling. And if you look at the glass, it certainly does not look very clear, and in fact, it looks kind of wavy. And that's because over time, the particles in the glass, the molecules in the glass, have been sliding past each other a little bit, and gravity's been acting like on them and kind of pulling them down a little bit towards the bottom of that pane of glass. And as a result, the glass looks kind of wavy. It doesn't look perfectly clear and transparent anymore. And you can't look through it and see things as crystal clear as you could when the glass was new. And if you ever have a chance to check out a really old building or an old castle or something like that, check out the windows. You may see that waviness. And I also know that glass windows in really old places are very brittle as well. The glass actually flows toward the bottom of that pane, and at the bottom they tend to be a little bit thicker. And at the top they can get quite thin, and that tends to them being a little bit more brittle. So that's kind of a cool aside about amorphous materials like glass. Now the last term or topic for today is allotropes. And allotropes are different forms of the same substance, same element, that occur in the same state. And so oxygen, for example, you know oxygen's a gas. We breathe it all the time. Its formula is O2. However, in our upper atmosphere, we talk about the ozone layer. And ozone is another form of the element oxygen that's also in the gas or vapor state. And its formula is O3, ozone. And so different forms made from the same types of atoms, but arranged differently. Oxygen that you're breathing right now is 2 oxygens bonded together, but ozone has 3. Another notable example is carbon. And carbon is a solid at room temperature. And there are actually quite a few different allotropes of carbon. But three notable ones that I have in the image here would be diamond, graphite, and soot. And if you look at how they're drawn, each of these black dots or circles is supposed to represent a carbon atom. And if you take a look at, sorry, get rid of this here. If you take a look at how they are arranged, even though they are all made of just carbon atoms, they have radically different properties. And if you think about diamonds, and we talk about, you know, what are they used for, what are they good for, we know that they are jagged and have that edge, and so they're good for cutting tools, as well as being, you know, used in jewelry. And if you think about graphite, they're arranged in little hexagonal rings in sheets, and so as you apply your pencil lead and shade things or write things, those layers of graphite just slide right off, leaving a mark on your paper. And then finally, the soot. If you think about the terms crystalline and amorphous, which we mentioned earlier, the first two allotropes, both diamond and graphite, would be considered to be crystalline because they do have a definite pattern and arrangement of atoms, but soot would be considered amorphous because it really is not put together in any way, shape, or form. They're just kind of connected in any random ways. So that's allotropes, different forms of the same element in the same state. That brings us to an end of our notes for today. Oops, I gotta get my smiley face on there. That's what I always do. Hope that you understood that material. Please see me if you have questions. Have a great day.